आज हम ये सीखेंगे कि कोवलेंट कंपाउंड्स में आयनिक कैरेक्टर कैसे डेवलप किया गया और द आयनिक कैरेक्टर इन कोवलेंट कंपाउंड्स सिमिलर टू covalent character in ionic compounds. We can also have ionic character in covalent compound. So let's see how ionic character in covalent compound is developed and how to find the percentage ionic character in a covalently bonded molecule. So the name of topic is ionic character in covalent molecules. So though the compound or the bond is covalent bond, in this covalent bond, in many of the cases we didn't have 100% covalent character. Along with this covalent character, some ionic character also developed in the covalently bonded molecule. So what is the cause of this ionic character in covalently bonded molecule? The cause of this ionic character in covalently bonded molecule is due to electronegativity difference between the combining atoms If there exists an electronegativity difference between the combining atoms, then there is known as polarization of the covalent bond. The polarization of covalent bond due to the electronegativity difference gives rise to the ionic character in the molecule. So due to this electronegativity difference, polarization of bonds takes place. Due to this polarization of bond, a dipole is developed. That means a positive pole and a negative pole. So we have this a positive pole and negative pole, that is dipole. So this development of dipole in a covalently bonded molecule is what we call as polarization of bond, and this polarization of bond is due to the electronegativity difference between the combining atom. So this polarization in a covalently bonded molecule due to electronegativity difference, this is the cause of ionic character. So the moment we have this dipole is developed, so this shows ionic character. Ionic character is due to the development of dipole, and this dipole is due to the polarization of bond due to electronegativity difference. So ultimately the cause of ionic character in a covalently bonded molecule is due to the polarization of bond due to electronegativity difference between the combining atoms. Now if the combining atom is having same electronegativity difference, then that is known as 100% covalent. If the polarization is there or if the electronegativity difference is there, then the bond will develop some percent of ionic character along with the covalent character. So we have developed this electronegativity in the previous lectures while discussing the periodic properties of the elements. We have defined this electronegativity. Now this electronegativity is defined as the tendency of an atom in a covalently bonded molecule to withdraw the shared pair of electrons towards itself. So due to this withdrawing tendency, that partial withdrawal of the shared pair of electron takes place, and if the electron is more towards a particular atom, electron density increases, so this will develop partial negative charge. Now since the electron is moving away from the other atom that has decrease in electron density, so this will develop partial positive charge. So suppose, look at this, we have this A and B. So we have the shared pair of electron between this A and B. So we can have two cases here. If the electronegativity of A is greater than the electronegativity of B, then what is happening is these shared pair of electrons, which was supposed to be placed exactly in the middle of this AB bond, is more shifted towards the A. This is not completely taken up by A, but this is more towards the A, because this A has strong withdrawing tendency. So A withdraws the pair of electrons towards itself. As a result, electron density on A increases. So as the electron density increases, this develops a partial negative charge. Full-fledged cannot be there, because if we have full-fledged, then that is 100% ionic. We are not having ionic compound, we are having covalent compound. In this covalent compound, some sort of ionic character develops. Now since the electron is moving away from B, electron density on B decreases. As the electron density on B decreases, B will develop some partial positive. This is what we call as dipole. A positive pole and a negative pole is developed. And this development of pole is known as polarization, and the cause of polarization is electronegativity difference. The other way could be, if electronegativity of A is less than electronegativity of B, then the shared pair of electron will be more towards B. Since electron is moving towards B, so this B will acquire partial negative, A will acquire partial positive. So either way, there is development of dipole, or there is a polarization of pole due to electronegativity difference. Now this dipole is a vector quantity. This is a vector quantity, and the direction of dipole is from positive to negative. This is the direction of dipole. This represents the positive terminal, this represents the negative terminal. So when A is more electronegative, the direction of dipole is this. Or if B is more electronegative, then this is the direction of dipole. Now, so we have a dipole developed. So we have to find the percentage ionic character in this. Theoretical जो consideration है, let's see. Now this is for rough prediction of percentage ionic character. So we have this AB, we have this A, B. If electronegativity difference between the combining atoms A and B is equals to 1.7 is a limiting case. So if electronegativity difference between A and B is 1.7, then we say this is bond is 50% ionic, 50% covalent. So we can have a rough prediction. If this electronegativity difference is greater than 1.7, we say more ionic, less covalent. But if the electronegativity difference is greater than 1.7, then we say less than 1.7, we say this is more covalent, less ionic. But if the electronegativity difference is equals to 0, then we say this is 100% covalent. So if the electronegativity values are given, we can just take this reference to find the percentage ionic character. So the reference is 1.7. This is for the rough prediction. The other way is, there is one more method. I'll give you the experimental method also. The second one is, Haney-Smith equation. So according to this Haney-Smith equation, the percentage ionic character in a covalent molecule is equals to 16 into electronegativity difference between the combining atom A and B plus 3.5 into electronegativity difference between AB square. So again look at this, somewhat more accurate value is given by this Haney-Smith equation. Based on this equation, if the electronegativity difference between the combining atom is given, then we can easily define this percentage ionic character. So for this we need to have electronegativity values, and for this we will be given the values in the literature. So this is one of the way by which we can predict what is the percentage ionic character in a given covalently bonded molecule. But the experimental value, how to define experimentally the percentage ionic character? So we have looked at this AB bond. Let's assume if B is more electronegative than A, so B will acquire partial negative, A will acquire partial positive. So we have a dipole, and a dipole is from A to B. So we represent this dipole. Say we have a positive pole, we have a negative pole. This is the distance between the positive and the negative. This distance, that is internuclear distance, that is known as bond distance or bond length, and let this distance be D, is the distance between this positive pole and the negative pole, and let the charge or the fraction of charge on these ions will be some percentage of the electronic charge. Then this, the magnitude of dipole, magnitude of the magnetic moment, this is defined as E into D, while E is the electronic charge. This is charge on the cation or ion, charge on cation and ion. Now for partial polarization, this will always be less than the electronic charge. So this magnitude of dipole magnetic moment, that is E into D, is electronic charge. These are distance between the dipole or the bond distance or the bond length. So this is generally defined in terms of unit. Unit is 1. This is defined in terms of dBy, dBey, simply written as capital D. So 1 dBy is equals to 1.8 into 10 to the power minus 10 ESU centimeter, electrostatic unit centimeter. This is equals to 3.336 into 10 to the power minus 30 coulomb meter. This is standard unit. So otherwise, in most of the case, this is written as dBy unit. So dBy is nothing but this magnitude of this electric dipole, that is the distance between the charge and the charge carried by the dipole, this product. This is defined as the dipole moment. Dipole moment, the magnitude of dipole moment is defined. Now look at this. This dipole moment, as I told you, this is a vector quantity. So since we have a vector quantity, so to define this resultant dipole, we have to take the vector sum. So the resultant dipole will be vector sum of all vectors present in the molecule. So for a molecule to be polar, so the point is, for a molecule to be polar, this dipole moment should not be having a zero value. So for a polar molecule, the magnitude of this dipole moment should not be equals to 0. If the magnitude of dipole moment is 0, then the molecule is known as a non-polar molecule. Now look at this. We may have more than one dipole in a given molecule, but the resultant vector may be 0. So just presence of this dipole is not a sufficient condition for a compound to be polar. What we are saying is the resultant dipole of all the vectors present in the molecule should be having either some final value, then we say this is a polar molecule. If the resultant of all the dipoles present in the molecule is 0, then the molecule is known as a non-polar molecule. So to define the polarity of the molecule, we have to find the resultant of the vectors present in the molecule. That resultant, if this is 0, then that is not polar. If this is something final value, then we say this is a polar molecule. So coming to this, we define this value. So from this dipole moment, we will define the percentage ionic character. Percentage ionic character is equals to dipole moment experimental is the observed value, or observed value divided by dipole moment theoretical into 100. So theoretical is when we assume the bond to be 100% ionic. So assuming the bond to be 100% ionic, we will find the theoretical value of dipole moment. The experimental is the exact value or the accurate value of the particular molecule. So we take this ratio of experimental or observed value by theoretical value and multiply this by 10. This gives you the percentage ionic character of the covalent bond. Now let's see how to predict whether the molecule is a polar or a non-polar molecule. Take this example, we will define this. Take this hydrogen molecule. So we have hydrogen, electronegativity difference is 0. So we said dipole moment is 0. There is no dipole. So we said this is a non-polar molecule. Take this, we say HCl. Now hydrogen and chlorine. Chlorine is more electronegative than hydrogen. So chlorine will acquire partial negative, hydrogen will acquire partial positive. So we have a net resultant dipole. So यहाँ पे dipole is not equals to 0. So HCl is a polar molecule. Now take this. Now let's compare this carbon dioxide and sulfur dioxide. So we have triatomic molecule, carbon dioxide and sulfur dioxide. Now based on this dipole moment, we have to prove their structures also. So take this very carefully. Carbon dioxide, so we have carbon oxygen bond. Now oxygen is more electronegative than carbon, so we have an individual bond movement. So this is one dipole, carbon oxygen dipole. On the other side, look at this, we have carbon oxygen. So oxygen being more electronegative, we have another bond movement, so we have second dipole. Now look at this, both dipoles are in opposite direction, so therefore the resultant dipole moment, that is the vector sum, this comes out to be 0. So look at this carbon dioxide molecule. Though the molecule contains two dipoles or the bond moments, but the resultant comes out to be 0. Hence the dipole moment is 0, so the molecule is linear. So dipole moment is 0 only when the molecule assumes linearity. Now take the other way, sulfur dioxide. So we have this sulfur dioxide, SO2. Sulfur oxygen. So sulfur oxygen. Oxygen is more electronegative than sulfur. So we have one individual bond moment, second bond moment. So we have two dipoles. The resultant, this is the resultant. So this resultant is not equals to 0. So sulfur dioxide molecule, there is a net dipole moment. Because of this net dipole moment, the sulfur dioxide molecule is a polar molecule. So net dipole is there. That means this is a non-linear. So based on this dipole moment, we can prove this structure also. If dipole moment is non-linear, so if dipole moment is 0, then this is not linear. If dipole moment is 0, so we say this is linear. Similarly, take this. Just compare this NH3 and NF3 molecule. So we have these two, NH3 molecule and NF3 molecule. We'll compare the dipole moment of NF3 and NF3. So look at this. We have this N, and this also has a lone pair of electron. NF3, the same structure, and nitrogen has got a lone pair of electron. Now we say nitrogen, hydrogen, this is something called what you call tetrahedral structure. So nitrogen, hydrogen, hydrogen is more less electronegative than nitrogen. We have this nitrogen, hydrogen dipole. Second, nitrogen, hydrogen dipole. Third, nitrogen, hydrogen dipole. So we have look at this three nitrogen, hydrogen dipole. Three dipoles are pointing towards nitrogen. So the resultant of these three is this. So this is the resultant of three nitrogen, hydrogen dipoles. On the other side, we have a free electron. So we have free electrons. So the direction of this free electron is in this mode. So this is for nitrogen, free electron. This is for nitrogen, hydrogen. Now both the dipoles are directed in the same direction. So this will add up to give you the resultant. So this resultant is not equals to 0. So on the other side, we have NF3. Fluorine is more electronegative than nitrogen. So the direction of dipole should be from nitrogen to fluorine. So we have three nitrogen, fluorine dipoles. So the resultant of these three will be downward. So this is the resultant for 3 nitrogen, fluorine. We have this nitrogen free electrons. So the resultant of 3 nitrogen, fluorine and the resultant of this nitrogen electron both are in opposite direction. So since both are in opposite direction, they will cancel out partially. Because of this, though the resultant will not be equals to zeros, but these two dipoles are in opposite direction, they will partially cancel out. Whereas in case of ammonia, the resultant for 3 nitrogen, hydrogen and nitrogen free electrons being directed in the same direction, they will add up to give you the more resultant. So as a result, we say the dipole moment of ammonia is always greater than dipole moment of NF3. So we say ammonia is more polar than NF3. We'll take up some more examples. Take this BX3, boron trihalide. We can have BF3, BCl3, BBr3, Bi3, boron trihalides. So in this boron trihalide, boron assumes trigonal planar. So halogens, fluorine, chlorine, bromine, iodine. Halogens is more electronegative than boron. So halogen being more electronegative, direction of dipole is boron to halogen. Boron to halogen. Now take this. We have boron halogen two dipoles. Resultant of these two dipoles is this is resultant of BX dipole. On the other side, we have this boron halogen. This boron halogen dipole is on opposite side. So these two dipoles are in opposite direction. So the resultant will be 0. So the molecule contains 3 dipoles, but the resultant dipole moment is 0. So BX3 molecule is a non-polar molecule. Though we have 3 dipoles, but the resultant is 0. Take this CCl4, carbon tetrachloride. Take this. This is Cl, this is Cl, this is Cl, this is Cl. Or we can take this CBr4, Ci4 or CF4, carbon tetrahalides. Halogen is more electronegative than carbon, so the dipole is from carbon to halogen. So the resultant of these 3 carbon halogen bond is downward, whereas we have 1 carbon halogen upward. So these 2 dipoles are in opposite direction. Since these are in opposite direction, so the resultant is 0. So CCl4, CBr4, Ci4, CF4, this is a non-polar molecule, though the molecule contains 4 dipoles. Similarly, we can have some more examples. Take this. We have this C. Suppose this is Cl. This is CCl. Now, identical groups on the same side, we say this is cis. Take the other way. With this hydrogen Cl, hydrogen. Identical groups on the opposite side of double bond, we say this is trans isomer. To trans means opposite side, cis means same side. Now if you look at this, carbon halogen, obviously halogen is more electronegative than carbon, so we have this dipole. Take this carbon halogen. Now these 2 dipoles are in opposite direction, so they will cancel up, so the resultant comes out to be 0. Look at this cis. This is carbon halogen dipole, carbon halogen. Both are in this direction, so this will add up to give you the final resultant. So this resultant cannot be 0. So when we compare the dipole moment of these geometrical isomers, these are known as geometrical isomers, having same formula but different geometry, same side cis, opposite side trans. So the dipole moment of cis will always be greater than the dipole moment of trans. So if we have to identify between cis and trans isomer, the one having larger value of dipole moment will always be the cis, and the one having smaller value of dipole moment will always be the trans. Similarly, we can have this CH3, this is hydrogen, this is methyl on the same side, this is cis, so we have trans, this is trans. Now again we have to confirm. So doubly bonded carbon is having more electron withdrawing than the single bonded carbon. This is doubly bonded carbon, more electronegative than the singly bonded carbon. So we have 2 dipoles, so that is the resultant. So this resultant will not be 0. Take another case, trans. So we have this dipole. We have this dipole. The two dipoles are in opposite direction, so the resultant is 0. So I can look at this. Dipole moment of cis is greater than dipole moment of trans isomer. So this is how we can differentiate between geometrical isomers take water molecule. We say water is a polar molecule or a polar solvent. So we have this OH bond, hydrogen oxygen bond. So oxygen is more electronegative than hydrogen. So we have this dipole. Hydrogen oxygen, again oxygen is more electronegative than this. So we have two vectors pointed towards oxygen and the resultant is upward. So this resultant is not equals to 0 since the water molecule has got a finite value of dipole moment. So we say water molecule is a polar molecule. Take this Cl, this is Cl. So this is what we call as 1, 2, 3, 4. 1, 4 dichlorobenzene, which is also known as para-dichlorobenzene. So take this to be the center of molecule. So we have this. So we have this, or we can say simply this is carbon Cl because Cl is more electronegative than carbon. So both the dipoles are in opposite direction. So this resultant will be 0. So this is a non-polar molecule. Take this. Where this OH, these can have two different forms. So look at this. With this. Now we replace this hydrogen of water by benzene ring. So we have this. Similar look at this. We have this. We can have one structure. So if you look at this, this is hydrogen oxygen. So this is the direction of hydrogen oxygen. Carbon oxygen. So we have this resultant for this bond. Similar look at this. This is hydrogen oxygen, carbon oxygen. So we have this resultant. Now these are two dipoles. So they are the final resultant is here. So though we have 1,4 position, here the 1,4 position is 0. But this is possible only when we have linear structure. This molecule is not a non-linear. This is a non-linear molecule. Because of this molecule, the resultant dipole moment will be 0. So we say this is polar molecule. Similarly, look at this. We can have this instead of OH, we can have OCH3 or OCH3. In both the case, the net resultant will be having some finite value, so the molecule will be known as a polar molecule. But since we are discussing about the vectors, we can also find the resultant of the vectors. Take this Cl, Cl, Cl. Now we'll find the resultant of these two. So now look at this, take this to the center of molecule. So we have a dipole here, we have a dipole. This resultant of these two dipole is here. Now we also have a dipole on opposite sides. So these two are in opposite sides. So the resultant is 0. So this is 1, 2, 3, 5, 6, 4, 5, 6. So 1, 3, 5 trichlorobenzene resultant is 0. If suppose this is the case, then look at this. we have this molecule. If dipole moment of carbon Cl is suppose 1.5 D, then what is the resultant? So look at this 135. These 135, they will cancel out. So what is left? This is left. So we have dipole, resultant, resultant. So these three will cancel out. So finally left is we have this. So dipole moment of this molecule will be 1.5 D by. So this is a polar molecule. Suppose look at this, we have this is dipole. Suppose we have this dipole, let this magnitude be mu1. We have second dipole, let's suppose this magnitude will be mu2, and this is the angle theta. Then the resultant will be equals to under root mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. So this is the vector sum of these types of vector. If the mu1, mu2 and the angle theta between them is given, then we can easily find the resultant dipole moment. So look at this, we have benzene molecule. So this is X, this is X. So 1, 2 position. So this 1, 2, which is also known as ortho. This is X, this is X. 1, 2, 3. 1, 3, this is known as meta. Then we have 1, 4. 1, 2, 3, 4. So 1, 4 is known as para. If suppose CX dipole, so we have this dipole, this is mu1. And look at this. So this ortho angle is 60. If we have this meta, this angle comes out to be 120. In case of para, this angle is 180 degrees. So therefore resultant for ortho, this is mu1 square plus mu1 square plus 2 mu1 mu2 cos 60. So cos 60 is half. So twice mu1 square plus cos 60 is half. So mu1 square. So this is 3 mu half or mu root 3. So for this meta, resultant is mu1 square, because this is mu1 plus mu square plus twice mu square cos 120. So cos 120 is minus half. So we have twice mu square minus mu square. So this is mu. For this mu para, the resultant is mu square plus 2 mu square cos 180. So this comes out to be twice mu square cos 180 is minus twice mu square. So this is 0. So when we compare this ortho, meta and para, so resultant for ortho is greater than meta greater than the pair. So when we have these types of case, so accordingly we can compare the values of these two. So this is how we define the ionic character in covalently bonded molecules. So again I am repeating, the ionic character in covalent molecule is due to the polarization of the bond due to electronegativity difference. This electronegativity difference develops a dipole in the molecule. So this dipole, being a vector quantity, will have to find the resultant of all the vectors. So just presence of a dipole in the molecule is not sufficient condition for a molecule to be polar. What we have to find is the resultant of all the dipoles. So if the vector sum of all the dipoles is having some finite value, then we can say the molecule is polar. Otherwise, the molecule is non-polar. So I have given you a number of examples here how we can compare the dipole polarity of the molecules, and from this polarity how we can develop or calculate the percentage ionic character. I have given you theoretical calculation as well as the experimental determination of the percentage ionic character. So this is all about the percentage ionic character or the polarity in covalently bonded molecules. Thank you.